Hey there, grade nines. Welcome to today's math lesson. We're at home today just because we've been sent home to be working. So we are in chapter 4, lesson 5. And in this lesson, we're going to be talking about using graphs to estimate values. So I'm going to do a little bit of screen sharing just because it's easier to use some graphs that are already drawn than draw them myself on a whiteboard. So let's get started. So let's start with this one. Here we have a population in a city in relation to the amount of water used. And this capital ML is different than a lowercase ml. These are called megaliters. So a megaliter is equal to 1,000 liters, or sorry, 1 million liters. So that's a lot of water. So here, when they have a population of 100,000, they are using 750 megaliters for the per month. When we have a population of 130,000 people, 975 megaliters. 180,000 people. So obviously, as the population grows, we're able to see an increase in the water usage. Now, this is something that's a little bit different because as we see, it's a linear relation because when we graph it, it makes a straight line, which is what we have below or to the right. But the difference is what we have in the population. So here we have an increase of 30,000. Here we have an increase of 50,000. And here we have an increase of 40,000 people. So it's hard for us to actually go about and determine exactly what the numerical coefficient is. We would actually have to try to get more information within it. So we might have to say, break it down between 100,000 and 130,000, and then take the 125 and divide that into a couple more, or sorry, 225 and break that down into a couple more groups. So we could actually figure out exactly how much more water is being used as people are being added. So what we can actually do is when we look at this graph, we can use this graph and try to determine certain things. So one of the first things it wants us to determine is estimate the monthly water usage for a population of 150,000 people. Well, as we see, we don't have 150,000 people on our input-output chart, but we can estimate. So this is broken up into 5 sections. So every section is roughly 200,000 people, or sorry, 20,000 people. So our actual 150,000 people is going to be right around here. So we can estimate by basically saying, and as we're going up here, this is about 250 megaliters. So it looks like it's almost right in between our 1,000 and our 1,250 megaliters. So that would be in between. So I'd say about 1,125 megaliters would be, in my opinion, would be a good estimate of where it might be if we have 150,000 people. The next is estimate the population when the monthly water usage is 1,400 megaliters. So that's going to be slightly below, okay, slightly below here, but it's going to be closer to the 1,500 than it will be the center line. So I'm guessing it's going to be probably somewhere around where this dot is, but probably a little bit over because that dot is at 180,000 people, and that's 1,350. So it's going to be slightly higher. So who knows? It's going to be maybe 180,000 or 180, 7,000, 185,000, something like that. And then predict the water usage for 250,000 people. Well, our graph only goes up to what we can say is 240,000. So what we need to do is we need to add another 100,000 to that, or sorry, 300,000 to that. Well, what I can do is I can actually take my difference here and add it. So I can take my difference from 750 to 975, which is 225, and I can add that to this because I need to add 30,000 to 250 or to 220 to get to 250. So my answer would be somewhere close to 1,875 megaliters. All right. So as we move down, this one might make a little bit more sense. So here we actually have a car that's traveling at a constant speed. So it looks like it's traveling somewhere, let's see if it actually tells us. I'm not exactly sure. No, it doesn't look like it does. Okay, but what we can see is in an hour, okay, it's under 100 kilometers. So it's going slower than 100 kilometers an hour. It looks like it might be going somewhere around 80 kilometers an hour would be my guess. Okay, so what we can actually do is we can determine how far the car has traveled after so many hours. Because every hour, if it's traveling at that constant speed, we can actually determine exactly how far it's gone. So here, as we move down, we can actually see if we're looking after an hour and a half, how far would it have gone? Well, here they're actually predicting probably about 120 kilometers, which seems like a good prediction based on that. And then how long would it take them to go 300 kilometers is their next question. Okay, the estimated time to travel 300 kilometers. So they're taking this and they're kind of extrapolating. So this is just a term that you'll use to get information from a couple points. So here we might say 3 hours and 45 minutes or 3.75 hours, okay? Because it would be kind of in between 3 and 4, all right? So we can actually use this information and then we can expand on it and try to get. So here we're talking about solving problems. So Jenna borrows money from her parents for a school trip. She repays the loan by making regular weekly payments. The graph shows how the money is repaid over time. The data are discrete payments are made every week. Okay, so how much did she borrow? Well, at 0, we can suggest that she borrowed what it was at 0. So at 0 weeks. So we can guess that she borrowed $200. How much money does she still owe after 3 weeks? So we'll look at 3 weeks and then we can kind of come up to here. And I'm guessing probably the same as you, $200 or $140. Okay. How many weeks will it take Jenna to repay 1/2 of the money? So if she had 200, so we're looking for 100. So it might take her 5 weeks. All right. And then we can kind of get more information from it. So based on those questions that we had, these are kind of the answers that we are getting. So we're getting the 3 weeks, and we're also getting the $100 would take 5 weeks, and she borrowed $200. Okay. And then here we're using extrapolation to solve problems. So this is when we're actually taking something and we're grabbing the information from it, and we're trying to expand on it as well. So Maya is jogging at a constant speed. So she's on a track and she jogs for 10 minutes. Assume Maya continues to jog at the same speed. She doesn't slow down. Okay, so here we can predict how long it will take Maya to jog 2,000 meters. Well, we only had her going for 10 minutes, but in the 10 minutes, it looks like she went 1,200 meters. So we could actually take some information from this. So we can take how long it took her to go 1,000 meters and we can double it. So I can guess that it took her to go 1,000 meters about 8 minutes and 8 minutes and 20 seconds would be my guess. So if we double that, so it might take her 16 minutes and 40 seconds. Predict how far she will run in 14 minutes. Okay, well, I can kind of do the same thing. So I can find a number that'd be easy to double. So let's take 7. Okay, 7 minutes. If I double this, then it should get me to 14 minutes. So in 14 minutes, it looks like she went about 850 kilometers. So I'm going to say she'd probably go about 1,700 meters. Okay, what assumptions did you make? Well, we assumed that she's able to maintain the same speed. We assume that she doesn't slow down and she doesn't speed up. So otherwise, if she did, the graph wouldn't be a straight line. So based on that information, this is kind of what we're able to determine. So some of the same information that we just had. All right. The last example that we're going to go through is when we're using a graph with a linear relationship. So determine the value of x when y equals 3. So when y equals 3, so we're actually looking here. Okay, we have to expand on this graph a little bit more. So we're actually going down. So when y equals 3, what's x going to be? So there's a couple things that we can do actually before we even get there. So let's annotate this one a little bit. So we'll actually try to come up with something. So I can actually come up with what my equation is going to be. So I know that my constant is going to be +5. Oops, let's see. This is going to draw for me. Oh, sorry, that's why I have it in white. So my is going to be +5. And then I'm trying to figure out what my numerical coefficient is. So I know that it's actually going to be less than 1, okay, because it's not at a 45-degree angle. So I'm going to use my rise over run. So my rise is 1. It goes up 1. So if I go from, if it goes up 1, it's moving over 3. So it's going to be rise over run. Okay, my rise is 1, my run is 3. So it's going to be 1/3 times 5. So what I want to do is I want to determine what the value of x is when y equals 3. So if I say 3 equals this, then I can actually go and calculate it. Okay, so I'll bring my 5 over to the other side. So I have to subtract 5. So then I'm going to have -2. Then I have to multiply both sides by 3. And I'm going to end up with -6. So when y equals 3, my x is going to equal -2. Okay. If I want to do it the other way, what's y going to be when x equals 5? I would put 5 in here. So I've got 5 over 3 plus 5. Okay. To try to actually calculate it for what y is. So 5 over 3 is 1 2/3. So that would be 6 2/3 over 5. Let me just clear this. Okay. So that's what they ended up getting. So I got -6 and I had 6 2/3. Okay, so it wasn't exactly at the end of a point, but it still worked out. So I'm able to use that information, basically substitute in the what I was able to determine to try to calculate exactly what's going on. Okay, I'm going to stop the video here. If you guys have any questions, make sure that you bring them to the Zoom chats. We're going to go over some practices with this, and then let me know through Hangouts if you need extra help. Good luck.